It's called Laplace transforms. And what these are, and these kind of link kind of in a similar kind of theme to the Fourier series, the Fourier transform, which we're going to look at as the third part of my unit. And for us, Laplace transforms are mainly a tool for solving certain types of differential equations. Okay. Now, a significant component of applied mathematics as a whole, and a significant component of our degree, if you look at the third year courses, a significant component of applied mathematics concerns the study of and solution of differential equations. Any kind of mathematical model you build of the real physical world, problems in engineering and physics, invariably the description of those problems comes in the form of a differential equation. And the quantities that you're interested in finding out the values of and modeling invariably or often are quantities measuring some kind of physical property, and you're interested in their evolution over time. So quite often what you end up studying is a differential equation involving time parameter t, and maybe some other spatial parameters and so on. And the object of the game is to solve that differential equation. Okay? That's the information you're looking for. And the two third-year courses, the course on computational methods for ODEs and the partial differential equations, numerical methods and partial differential equations. What those courses are concerned with is the numerical solution of differential equations. So numerical solution refers to the situation where you cannot solve the differential equation exactly. You can't solve it on paper and pencil and get out a nice formula for the solution. It has to be solved instead using approximate methods, okay? Using computer algorithms that find approximate solutions to the differential equation. So if you're trying to find the position of a particle moving in some kind of force field, you've got a differential equation for that. The computer can supply approximate estimates for the position of the particle at any time t in the future. And there, a large part of the study is studying the behavior of these approximate algorithms, how well they converge, or at what rates the estimates will diverge from the real answer as time goes forward, and so on. So most interesting differential equations can't be solved exactly. But in this chapter, we're going to concentrate on a class of differential equations that can be solved exactly. All that term. So ordinary differential equation refers to the fact that it's just a function of a single variable. linear combination of two functions, y1 and y2. The left-hand side constant coefficients means the things multiplying the derivatives are just constants, real constants. So we got a0, a1, etc., up to an. It would be more complicated if those functions themselves were functions of this variable t. That would be more complicated. That would be a differential equation with non-constant coefficients. Although we do slightly weaken that, we do allow the, see I've got this g of t over on the other side. This is, if you like, if you're interpreting the whole thing as a collection of derivatives of y, then the g of t is, if you like, the constant coefficient, but it's not a constant in the normal sense. G of t there is itself some kind of function of time. And the Laplace transforms is a toolkit that will allow us to solve these equations, so find out what the function y is, for as long as the function g is reasonably well behaved. So as long as the function g is a function that we can understand quite well, what that will mean is that it has a Laplace transform. Then, in principle, the Laplace transform method allows us to solve any equation like this. Okay? So that's just looking at some of the collection of things that we will be solving. And now let's introduce the idea of a transform itself. Okay? And in order to do this, I want to just give an analogy with some properties of the logarithm. Okay? But before we meet the Laplace transform itself, we'll consider the behavior or properties of the logarithm transform. Well, really what I mean is the logarithm function. The logarithm function, yes, we'll take it here. I'm talking about, well, I could be talking about the logarithm function to any base. Talk about the natural logarithm function, logarithm to the base e, or logarithm to the base 2, logarithm to the base 10, any kind of logarithm. What I'm about to show you is that this was one way that logarithms were used a lot in practice before we had available to us mechanical or electronic calculators or computers. Okay? So this is the way that the logarithm can be used to simplify and estimate answers to arithmetic problems. Okay, so the logarithm, one way of viewing the logarithm is that it's a device that can allow you to do this, to simplify arithmetic problems and to get estimates for their answers. So suppose you wanted to work out a power like this, a to some power b. Or you wanted to work out, say, a multiplied by product. Well, for the moment, we think of these as hard problems. Okay? Raising a number to a power or multiplying two numbers as kind of, it's difficult. And if these numbers were complicated, if they were very, very large numbers or numbers to a high precision, numbers with a lot of decimal place is given. Doing the powers and multiplying them is, okay, you can do it, you can sit down and do it on paper, but it's, for numbers with a lot of information in them, it takes a lot of time. But if we apply the logarithm to these, then they suddenly look a little bit easier if we're willing to work in terms of logarithms. Because the well-known property of logarithms is that the logarithm of the power comes down and simply multiplies the logarithm value. Also, if you take the logarithm of a product, a times b, it becomes the sum of the individual logarithms. So in each case, the hard operation, raising to a power here, has been replaced with an easier operation. Here we just have to multiply together two functions. Or in the case of multiplication, the harder problem of multiplying has been replaced by an easier problem of addition. So we consider the things on these sides as easier problems. So we could evaluate this easier problem of multiplication here to get an answer. Let's call this answer 1. Or we could carry out this sum here to get an answer, call this answer 2. So we got these two answers, answer 1 and answer 2. Answer 1 and answer 2. What do we do with them? Well, we're not so much interested in the solutions to these problems. Really, we want the solutions to these problems. So we want a transformation which goes back the other way. Okay. And, well, this would be the exponential function. Going back the way, this is the inverse of the logarithm function. Okay. And so the answer to this problem of what you get when you multiply a times b, this will be the exponential of answer 2, what we have here. And a to the power b will be the exponential of answer 1. So the logarithm allows you to replace harder operations with easier ones. As long as it's not, it's not so amazingly straightforward. You do need to be able to calculate the logarithm values and the exponential values. So it allows you to replace harder operations with easier ones, as long as we can calculate, or at least approximate, values of the logarithm function. Now, I realize this idea of the logarithm function might not be so much within your cultural experience. It was just about in mine. When I was in school, we were kind of little part of the schooling, calculators were not yet widely available. This would have been about 1980s, early 1980s. Just when I was starting to do complicated arithmetic in schools. And we did, well, I think I was about the last generation, or the last group of kids, before calculators became easily accessible and widespread. So they maybe just about had to use this, had to actually use the logarithm transformation like this sometimes. It was still being taught anyway. And I'm sure you've seen, to the picture up. Log tables. They're not these ones, but yeah, these ones here. So, I mean, you're still familiar with this kind of idea in your probability and statistics work. Those of you doing probability and statistics units, you make use of tables for showing you values of probability distributions. Still using those. Those have kind of lingered around. Yeah? People don't really, students are still taught how to use those, and it's still a requirement that you understand how to the idea of reading and using distribution tables. But so these kind of tables, so I would have actually been taught how to use these. These just contain lists and lists and lists of pre-calculated values of the logarithm function, okay, for numbers of various precision. And going along with these, there would have been tables of the exponential function, which go back to the other. Okay. And it was actually something you did, that if you wanted to multiply together or get an estimate, if you wanted to get a quick estimate of the product of two numbers, which had a lot of information, either the numbers are very large or the numbers had a lot of decimal places, you could look up their logarithms, look up the logarithm of a plus b, then add together two logarithm values, which would be considered a trivial operation, you do really quickly. You get a certain answer, and then you look up the exponential of the answer, or you look up, you use the logarithm table in a reverse kind of way. Same table. To get the exponential of answer 2, which would be the product you were originally looking for, or at least an approximation. Okay. Now, why am I showing you this? Well, I'm showing you this because the Laplace transform method for solving differential equations fits into this kind of viewpoint. We start with the consideration of a hard problem, which is solving the differential equation. And there's no very quick and easy way to do it. Okay? No simple algebraic manipulation that gets you the solution. So, now we don't use the logarithm, but we use the Laplace transformation. So the Laplace transformation is some kind of transformation which converts the problem into a different problem, but one which is easier to solve using algebraic manipulation. So we transform the problem into a slightly different setting. We then solve the problem in the different setting, and then take an inverse Laplace transform at the end to get back the original solution, to get back the solution to the original problem, to the original differential equation. So that is how the Laplace transform operates. Yeah, so you start off the hard problem that we have. Hard problem that you have here is to solve some differential equation. So let's say, let's kind of write out a general one. It would be an times the a derivative of y plus all the way down to a1 times the derivative of y plus a naught y, maybe that could be equal to my g of t. So this is like this is the differential equation, or the format of a general linear ordinary differential equation of constant coefficients, which I showed you on page 29 a few moments ago. So here we're using the different notation for the derivatives. So the y with the superscript, the bracket, superscript and bracket means the nth derivative of 1, and so on. So that's the hard problem. We've no hope of solving that quickly and easy to get y of t equal to something. Just going immediately from the differential equation to the solution is kind of hard. can't really be done. Okay? There's no general way to describe that in simple terms. Okay? So instead, we have this transformation, which is the Laplace transform. And it's represented with this curly L, like a script handwriting, calligraphic L. That's how we normally denote it, just to make it stand out from any other function, something like that. So use a calligraphic font or a handwriting font. What does that do to the differential equation? Well, it keeps it as an equation. It's still going to transform the equation to another equation. But it'll no longer be a differential equation. And just to keep it compact a bit. Instead, it'll be a more kind of algebraic equation. Brings it over into this kind of form. So here, on the left-hand side, we've got a summation, which is kind of mirror tracking the summation in the differential equation on the left-hand side. I've got these unspecified functions for now, capital AJ of S. But these capital AJ of S, these are polynomial functions, polyfunctions in S. This G function here is the transform of G of T. So the transform takes a function in the time variable T, and it gives you a function in the new variable S. We'll explain that when we look at this example. And this function here, capital Y of S, this is the transform of Y. Of course, that's unknown to us, because we're trying to solve the original differential equation for the function y. So we don't know what y is. So we don't know what this capital Y is, capital Y of S. But, if we assume it exists for the moment, or we can use it there in a limited sense. The key thing to recognize here, you can even see simplification happening here, is that over here on the left, we have different derivatives of the unknown function y. But in taking the Laplace transform, all of these different derivatives have all been replaced by the one function, capital Y of S, which is the Laplace transform of Y. Now they pick up the complication implied in taking a higher derivative of a function. That goes into this polynomial function in S. Okay. So it's not the case that each different derivative transforms to exactly this function y of S, which is the transform of y. But each different derivative transforms to a different multiple of capital Y. You've got a different polynomial function. But anyway, we'll see all this in full detail shortly, in the next few lectures. Now this problem can, in principle, be solved algebraically. Solve this algebraically to get a solution for the function capital Y of S. Okay? So this will be, well, let's say a function in S just. So you transform the problem into a slightly different looking problem, but still kind of mirroring the original one. This one admits a solution by relatively straightforward means, just using algebraic manipulation. So you solve the transform problem, and then you bring this one back with the inverse Laplace transform. Inverse Laplace transform. And this brings you back to this brings you back to your solution y2. So this is the way, or just a kind of broad map of how the Laplace transform will work. We want to solve this differential equation at the top left. We can't solve it directly just by going down straight the left-hand side by any kind of simple techniques. We must change the problem to a related problem in a different setting, featuring these functions of this new variable s. This one can be solved in principle relatively straightforwardly to get its solution, capital Y of s. This capital Y of s is representing the transform of the original unknown function, little y. And then we take this inverse transform, which goes in the opposite direction, which is the inverse of the original transform, and this brings us, this one brings us back then to the function y of t, which solves the original problem. Okay, so let's have a look at the notes and actually have a look at what this thing looks like, what actually is the transform. So this is the definition of the transform here, definition 2.1. Okay, so if f is a function defined on positive real numbers, the Laplace transform of f is a function. It's a function of a new variable. The new variable we normally denote by s. Okay? We have different kinds of notation that are used. So some of those are given in 2.5. We can either use this curly L, calligraphic L of f, or sometimes we use the original function letter, which would be a little f here with just a bar across the top of it. Or there's also a convention, which is what I was using in my handwritten sheet there, that we use a lowercase letter for the original function and the uppercase letter for its transform. Okay, so you could also call the Laplace transform of little f here capital F. And the actual definition that it has is an integral transform, and we're integrating this exponential here, e to the minus st. So we're integrating e to the minus st multiplied by t, and integrating this with respect to t across the whole range from 0 to infinity. So we're kind of integrating out the variable t. Or we're kind of summing up, all the values of f. It's a weighted sum of all the values of f, weighted by this factor e to the minus st. And what we're going to be studying in this chapter is studying this transform, working out what it is on various well-known standard functions f, and also investigating it for its properties. Looking at what properties the transform has, and how these properties combine together to allow you to solve the differential equation that you apply it to. So you can see over the page we can look at a bunch of Laplace transforms. So this page and the one following it are extracts from the standard examination formula book that you'll have. So this will be something you'll be using in the mathematics exam. So this table lists on the left-hand side, we've got a lot of standard functions. T, so a constant function 1, function t itself, the identity function, t to the n, exponentials, sines, cosines, etc., products of exponentials and sines. Then some other ones you might be familiar with, the Heaviside function, or the unit step function, we'll be learning about that. The Dirac delta function, delta. Then on the second page it lists, well, these are a number of properties of the Laplace transform. So we'll kind of be working our way through a lot of these results that are listed here in this table. You can see what the transforms look like. So the constant function 1 has a transform 1 over s, the reciprocal function of s. The function t has a transform of 1 over s squared. In general, t to the n has a transform n factorial over s to the n plus 1. So it transforms polynomials to powers of the reciprocal. Okay, but a function of a new variable s. The exponential goes to 1 over s plus, well, whatever this coefficient is, but the negative of the coefficient. The minus a here transforms to plus a here. And so on. So you get these kind of polynomial, or sorry, not polynomials, but rational functions in it. Notes on definition 2.1. So the Laplace transform of our function f of t it has a transform like this, which is the integral from 0 to infinity of e to the minus st f of t dt. Well, one question which arises is, see, this is an infinite integral. So when you're integrating across an infinite range, you have to think about, well, does the integral converge or not? Oh. So what about convergence of this? Because it's an infinite integral. So it might not converge. Well, we'll look at a little bit of the detail here as we go through it, and as we look at proofs of the properties that the transform has, and look at the transforms of some standard functions. In general, the new variable s is complex. It's complex variable s. We think of the function t, we generally think of the function t as a time-like variable, so just being a real variable for the original function f. But the variable that appears in the Laplace transform is s. This, in general, this can be a complex variable. Well, if s was equal to a plus ib, a and b being real numbers, then e to the minus st, that would then be equal to e to the minus at times e to the minus ibt. Yeah, because you'd have, okay, so I kind of skipped a step there, but you replace the s on the left-hand side here with a plus ib, multiplying t, but then you've got an exponential of sum, so that will split up as the product of the exponentials. Exponential of the sum here, so where s is replaced sum that was split up as the product of the exponential. Now note that the second factor, e to the minus IBT, note that the absolute value of e to the minus IBT, this is equal to 1. Okay? Since e to the I anything is an element of the unit circle. The unit circle in the complex plane. Unit circle centered at 0. So that always has absolute value 1. So the absolute value of e to the minus st then is equal to the absolute value of e to the minus at. So the size of e to the minus st is governed by the real part a, which is the real part of s, the real part of the complex variable s. And what you can see here is that for positive a, which is the real part of s, e to the minus st will converge to 0 as t goes to infinity. So at least for values of the complex variable s which have positive real value, that exponential does converge to 0 as t goes to infinity. So as you're integrating from 0 to infinity on t, that factor e to the minus st that you're multiplying the ft by, this factor is going to 0, is converging to 0. And it converges to 0 quite fast. Just so, exponentially fast. Which is certainly faster than any polynomial can converge to 0. And fast, in terms of looking at standard families of functions, the exponentials converge to 0 like that relatively fast. So for a large class of functions, f, the term e to the minus st f of t, this will also converge to 0. Will also converge to 0 as t goes to infinity for most, let's just put in brackets, most positive values of a, which is the real part of s. Sometimes we'll have to shift it a little bit further than just saying it has to be bigger than 0. Sometimes we'll require it to be bigger than some certain number. But then for any value bigger than that number. So for a large class of functions, this term that we're integrating will also converge to 0. And so just because it converges to 0 doesn't mean the integral is convergent. You can still have things like the harmonics, like remember the harmonic series, the reciprocal function which converges to 0, but still it has an infinite integral. But at least if it's converging to 0, the thing you're integrating has a chance of, the integral has a chance of converging. So a large class of functions, this term converges to 0 as t goes to infinity for most positive values of a. And so the integral 0 to infinity of e to the minus st f of t dt will have a chance of converging. So that's kind of just a kind of broad, rough argument to say that a lot of functions will have Laplace transforms. the Laplace transform will exist for a lot of functions. Okay, so that's one big job of work we have to do is to find out Laplace transforms for our standard kind of family of functions that we want to be able to study. And that'll be one task. The other task will be investigating properties of the transform. Okay? So a lot of the results that you see in the early part of this chapter, or spread throughout this chapter, are properties about how the Laplace transform behaves in general. Okay? So we will study the Laplace transform of f for various standard f, various standard functions f. That's one thing we'll study, and we'll also study properties of, general properties of the Laplace transform. There's only 2 minutes left, but the first general property we can probably knock off straight away, such as linearity. What would linearity mean? Linearity, you're used to studying that with Stephen in your algebra. This would refer to taking the Laplace transform of a linear combination of 2 functions. So if you're considering functions f and g, if I have functions f and g that have Laplace transforms, so functions f and g for which those integrals converge, what is the Laplace transform of alpha f plus beta g? Now what you'd expect, or what you'd like it to be, is equal to alpha times the Laplace transform of f plus beta times the Laplace transform of g. That would be linear behavior. This will be nice behavior. You take a Laplace transform of a linear combination of stuff, you get the corresponding linear combination of transforms of the stuff. Alpha times the Laplace transform of f plus beta times the Laplace transform of g. And this really is not hard to prove once you make use of the linear behavior of integration itself. Really, it's just a way of saying that integration is a linear operator. Okay. We can split this integral up. As long as the individual integrals exist, okay, so it's just really like a one-line proof. Right? Just taking the Laplace transform of that linear combination of functions, f and g, then just recognize, oh, well, really I'm just integrating a linear combination of stuff. Integration is linear. I can split up the integrals like that, and then just by looking beta times transform g. So even before we found out that any Laplace transforms exist at all, we haven't actually found any of these for any simple functions. But you can see a nice property that the transform is going to have. Okay. So this step here is the linearity of integration. Okay, I better leave that there for this morning. So we'll continue with this. I'll just do a little bit more on it next week. I'll also do some revision stuff next week as well. Some exercises, some exam questions. But this will occupy us for the first half of term 2. First part of term 2 anyway.